artificial intelligence has an unexpected problem. It isn't just electricity. It isn't just computing power. It's heat. Every calculation performed by a modern AI system eventually becomes physical heat. And as computing becomes more powerful and more concentrated, managing that heat becomes increasingly difficult. For decades, data centers could rely primarily on air, fans, chilled rooms, traditional cooling systems. But the density of modern computing is changing the equation. More processing power is being concentrated into smaller physical spaces, and that means more heat has to be removed from the same amount of infrastructure. The solution is increasingly moving from air towards liquid, and liquid cooling needs something the digital economy cannot manufacture: water. And this is where the story becomes interesting, because when something that was once treated as a utility becomes a constraint, ownership starts to matter. For most of the digital era, cooling was largely invisible to investors. You built the data center, you connected it to electricity, and the cooling system was simply part of the facility. But AI is changing the economics. The more computing capacity concentrated into a facility, the more heat that facility has to manage. And that creates a physical constraint that software alone cannot solve. A model can become more efficient. A chip can become more powerful. Algorithms can reduce the amount of computation required. But whatever computation remains still produces heat. That heat has to go somewhere. Historically, one of the most common ways of managing large thermal loads has involved water. Cooling towers can use evaporation to remove heat efficiently, but evaporation means water is consumed, and that creates a very different problem in regions where water is already under pressure. Technology companies may be able to build a data center in 18 months, but they cannot manufacture a river. They cannot instantly increase a region's water supply, and they cannot assume that a municipality will provide unlimited industrial water indefinitely. This creates a new form of infrastructure risk. The question is no longer simply, can you build the facility? It becomes, can you keep the facility cool for the next 20 years? And that is where ownership enters the equation. When a resource becomes constrained, there are usually two ways to respond. You can compete for more of the resource, or you can build systems that require less of it. That distinction is important, because the opportunity isn't necessarily in owning water itself. It may be in owning the infrastructure that makes industrial computing less dependent on scarce water. And that creates two ownership layers worth watching. The first is closed-loop thermal infrastructure. Instead of continuously consuming large quantities of water through evaporative systems, newer cooling architectures can circulate liquid through a closed system. Direct-to-chip cooling can move coolant directly to the components, generating the greatest amount of heat. Heat exchangers can then transfer that thermal energy away from the computing equipment, and closed-loop systems can repeatedly circulate the cooling medium rather than constantly replacing evaporated water. The important investment idea isn't simply liquid cooling will grow. It is this: as thermal management becomes more important to the economics of computing, the infrastructure that manages heat becomes more valuable. The cooling system moves from being a background facility expense towards becoming part of the critical infrastructure that determines whether the facility can operate at all. You don't necessarily need to own the data center. You can own the infrastructure that allows the data center to function. The constraint becomes the asset. The second ownership layer is private water and reclamation infrastructure. Even with more efficient cooling, some industrial facilities will still require significant quantities of water. Instead of relying entirely on municipal drinking water systems, industrial facilities can increasingly look towards alternative sources. Wastewater can be treated. Industrial water can be recycled. Non-potable sources can be used where appropriate. And water can be circulated through increasingly sophisticated treatment and reclamation systems. This changes the ownership model. The valuable asset isn't necessarily the water itself. It can be the infrastructure that makes water available, treats it, recycles it, and returns it to the industrial process. Think of it as a private layer sitting between scarce natural resources and industrial demand. If a facility can recycle water internally rather than competing for fresh municipal supply, its dependence on the external system falls. And if that infrastructure is owned by a third party, the owner can potentially earn long-term infrastructure revenue from the industrial users that depend on it. That is a very different proposition from simply betting on the price of water. Understanding the chain changes the question you ask. AI creates demand for computing. Computing creates heat. Heat creates demand for cooling. Cooling creates demand for water and thermal infrastructure. And every additional constraint creates another potential ownership layer. This is why looking only at the technology companies can be misleading. The obvious companies are often the ones creating the demand. The less obvious opportunities can sit underneath them. The companies, landowners, infrastructure operators, and specialized asset owners that control the resources and systems required for the technology to operate. That is the ownership layer. And this is exactly where the investment question changes. Investors don't ask only, who is going to build the next generation of AI? They ask, what does that AI economy become dependent upon? Then ask, who owns those dependencies? Of course, none of this means every cooling company, water infrastructure business, or reclamation project is automatically compelling. There are serious risks. Liquid cooling is still an evolving engineering field. Retrofitting existing facilities can be expensive. Different chip architectures require different thermal solutions. Water infrastructure is heavily dependent on local regulation and geography. Water rights can be politically sensitive, and infrastructure projects can require enormous amounts of capital before they generate meaningful returns. It is also worth noting that the water infrastructure thesis depends heavily on geography. A data center in Iceland has very different water constraints than one in Arizona. Regional specificity matters more here than in almost any other infrastructure thesis we have examined. There is also an important distinction between owning a scarce resource and owning infrastructure that helps manage it. They are not the same proposition. The thesis isn't that water suddenly becomes the next speculative commodity. The thesis is that as physical constraints become more important, the infrastructure controlling those constraints can acquire strategic value. If you only view artificial intelligence through a digital lens, you see models, applications, software, data, but underneath all of that is a physical machine. Technology creates demand. Demand creates constraints. Constraints create infrastructure, and infrastructure creates ownership opportunities. The important question isn't simply what technology wins, it's what does that technology make indispensable? Because that is where the ownership layer begins to appear. Technology creates value. Ownership captures it. The next phase of the AI economy may not be defined by who owns the most computing power, but by who owns the infrastructure that computing cannot operate without. This is the Pivot Compass. Subscribe. Position yourself where structural momentum is building. And we'll see you in the next briefing.